All right, guys, so this is chapter 21. It's about energy metabolism and growth, and largely how hormones control growth. So let's take a look at the cartoon. Obviously, is sort of referring to the use of hormones in cows. So the growth hormone in cows, you can see the udders. Let's take a look at our first topic here. So our first topic is, what do we find in the bloodstream, right? So we're going to take in energy in the form of food. Our food molecules are going to be broken down by our digestive tract into its monomers, right? Its precursor kind of building blocks. And so in the blood, in terms of carbohydrates, you're going to find monosaccharides in the blood, especially glucose. We know that fructose is also a monosaccharide, and it's going to be found in the blood as well. It's transported into the cells as well, but primarily we're transporting glucose. So we see that we have glucose molecules in the bloodstream. They're taken into the body by glucose transporters. We'll talk about those in a little bit. And then we're going to use the glucose to make energy, right? So through cellular respiration, primarily the use of glucose is going to be oxidative phosphorylation. We're going to make ATP. We can use glucose for other as a metabolite for other things. We won't go into detail there. And then for some cells, it can be stored as glycogen. Proteins are going to be found as amino acids. So when proteins are broken down by the digestive tract, the amino acids are what you're going to find in the bloodstream. And so the cells will take up amino acids, again with transporter molecules. And then once amino acids are in the cells, right, they can actually enter, we talked about this in the first unit, they can actually enter into the cellular respiration pathway. So they can also provide energy, ATP for the cells, and they're going to be used as building blocks to make proteins that the cell needs, right? So proteins are actually constantly built up and broken down. So there's a great turnover for proteins in the cell. So amino acids coming in can be used to make those more proteins. Now, when you catabolize amino acids, you're going to produce ammonia. So ammonia is toxic, so you can see the ammonia here. Ammonia is going to be transported out of the cell. It's going to enter the bloodstream, travel to the liver, right? So this cell over here is the liver. And then your liver is going to change the ammonia into a harmless molecule, urea. The urea then will be excreted in your urine. Fats are interesting. So because fats are hydrophobic, right? They don't want to dissolve in water, or the plasma of blood is water. So they are actually going to travel in the bloodstream in packets. Those packets are called lipoproteins. And there are different kinds of lipoproteins. There's HDLs, high density lipoproteins, LDLs, low density lipoproteins. We're going to discuss those a little bit more in the digestive system. But just for a quick glimpse at what is a lipoprotein, so we can see that it is basically a micelle, so it's a single layer of phospholipids, and it's going to have some proteins involved, and then inside is where you're going to have all of your fats, your triglycerides. Remember, the word triglyceride is what we refer to as fat. So the triglycerides, along with other cholesterol and the fatty acids, are going to be found inside of this lipoprotein. And your body will make several types of these lipoproteins to carry the fats around your body. The one kind that's made from your digestive tract is called the chylomicron. So the chylomicron, you can see, is very different looking than the other ones. And then we'll talk about how some are considered bad and some are considered good, but not in this chapter. So anyhow, just to give you guys an idea of, your triglycerides are actually transported into your bloodstream in these lipoproteins, and the uptake into cells. So coming back to this picture, right? So here's our lipoprotein. And how do you get those triglycerides out of the lipoprotein? Well, there's an enzyme. So it turns out there's an enzyme on the capillary wall. So you can see how this LPL, that is lipoprotein lipase. And it's going to break open the lipoproteins, and it's going to liberate your fatty acids. So your fatty acids found inside can be in the form of monoglycerides. It can be in the form of fatty acids. This enzyme is found both on the capillary walls and also can be found on cell membranes. These enzymes, LPLs, are especially rich on the adipocytes, right? So your fat cells, and they're especially rich around the capillaries around fat, around adipose. So you're going to find a lot of breakdown of your your lipoproteins around fat cells, and then you can see that the fatty acids are just going to be broken. They're going to be taken into the cells by diffusion because they're going to be lipophilic, so they readily dissolve through the plasma membrane. And once you the fatty acids come into the cell, you can utilize them, right? So fatty acids are coming into the cell. You can enter into the cellular respiration pathway to make ATP. You can build more fats, make triglycerides, and then you can use those fats and break them down again. And then those fats can be the fatty acids and the glycerol can be liberated into the bloodstream. So all of these, food groups that give calories, right, that have energy content in them, this is the way that they are sort of traveling the bloodstream, and they are enter into the cells. They all have their sort of special job. They all can, if you look at the trend, right, they all obviously can make ATP. They all have energy, potential energy in the chemical bonds. And then there's ways to store them. The only sort of macromolecule here that is not stored, or it doesn't play a big role in energy storage, is proteins. We'll talk about that in a second. So let's take a look at the energy balance here. So just a quick, this is what I was talking about a little bit. So this is a table of your carbohydrate, protein, and lipid processing. How they are absorbed from the GI tract, how they are found in the bloodstream, how are they stored, right? So this is just, take a look at this. So carbohydrates, right? We know that glucose is stored as glycogen. We know that glycogen is stored primarily in the liver and the skeletal muscle. But out of our total energy stores of our body, right? The total percentage of total energy stored, glycogen only is a very, very small amount, 1%. We have a lot of energy stored as protein, right? So if we look at the proteins, our proteins are stored in skeletal muscle. And this is going to be 22% of our stored energy. But I have down here that in terms of liberating that energy and using protein as an energy source for your body, it's not a significant source of energy because your body does not want to break down protein. It's going to first use carbohydrates, then it's going to use the fat stores, and then the very last thing your body's going to do is going to use protein for energy. Because once you start breaking down proteins, you're going to start for your cells, right? Proteins play such an important role in they are enzymes, they are transporters, they are, the secondary messenger systems. They have such important roles in the cell that once you start catabolizing proteins, you're going to start to interfere with the cell's normal function. And that's bad overall for the whole organism. Like, you're going to die. Or severe muscle wasting. So that's not good. You're only going to do protein catabolism for energy in very, very extreme times, such as starvation. And if you look at our lipids, right, we know that the lipids are triglycerides, are fat stored in our adipose tissue, and this is going to be the major energy store for our body. All right, so moving on to energy balance. So this is, a nutrition label. You can see that this is something we look at every day. And just a quick word on the calories. So your energy input to your body is measured in calories. And the calories, or how much energy is in a certain food, is actually measured by something called a calorimeter. And that actually burns the food item. It burns 1 gram of the food item, and it measures how much it changes the temperature of water. So a calorie has this very strict definition, but in terms of food labels, it's a capital C. The capital C calorie is actually 1,000 little c calories, or you can think of it as a kilocalorie, right? So your food packages use the capital C calorie. So if we look at what's going on here, let's look at energy input. So we know that we absorb our nutrients. We just looked at, what we talked about, our nutrients coming into the bloodstream from our GI tract. Then our cells transport those monomers into them, and then we'll use those in different ways, primarily through, cellular respiration to make ATP. Energy out, right? So if you have an energy balance throughout the day, the energy that you take in the form of calories, if it equals the amount of energy that you put out during the day, then you have something called energy balance, and you neither gain weight nor lose weight, right? You maintain your weight. This energy balance is controlled a lot by your endocrine system, so we'll talk about different hormones. And again, energy input is just the consumed nutrients that you eat, and then the output is broken into heat and also work. So anytime you have a chemical reaction happen inside your body or in the universe, anytime there's a chemical reaction, a little bit of heat is lost. And that's just, the law of entropy. You're going to lose some heat. So your body, the trillions of cells that you have, are all humming with these chemical reactions. So you're radiating a lot of heat. You're producing a lot of heat. And so a lot of the food that you take in, those calories, are going to produce heat. And then, of course, the other 40% is going to go into doing work. What kind of work? It's broken into mechanical work. So mechanical work is like physical moving, like muscle contraction, moving your body, walking around, right? Speaking, using your tongue, using your diaphragm. So mechanical work, or the beating of cilia in your respiratory tract. Chemical work would be just chemical reactions. And then transport work would be the transporter systems we talked about, the sodium-potassium pump, moving things across the membrane, exocytosis, endocytosis, things like that. So transporting molecules, vesicles moving molecules from one area to the other area of a cell. All right, so let's talk about your metabolic rate. The definition of the metabolic rate is how much energy is expended per unit time. So this can be anything, right? So you can talk about your metabolic rate while you're sitting watching TV, your metabolic rate while playing basketball, your metabolic rate jogging a 10-minute mile. So it's per, it's just like how many calories are you expending per minute, per hour. You can just use whatever you want. So it's how much energy you're expended per time. Now, the basal metabolic rate is how much energy do you need to expend if you're awake, right? You're just laying down, you're not doing anything, and you fasted for 12 hours. So let's say you knocked out, you were in bed for 12 hours, you woke up, and you're just laying there in bed. That's your basal metabolic rate. And if you just stayed like that all day, every day, it's the minimum amount of energy you need to just stay alive, right? So your body, just to maintain the tissues, to maintain the chemical reactions, you do need a certain amount of energy, and that's your basal metabolic rate. So represents the minimum amount of energy expenditure necessary to maintain your body functions, basically stay alive, right? All right. So, and then once you start doing something, even if you start talking, your metabolic rate will go up. So how many calories you need is going to go up, and more activity equals a higher metabolic rate. So you can see here that your sort of energy rate, right? Your metabolic rate is your basal metabolic rate, just how many calories you need to survive the day if you just expend zero other energy. Thermogenesis, just to keep your body temperature the same, right? And then adding on top of that any physical activity that you do. All right, so let's take a look at negative and positive energy balance. So this should make sense to you guys. So we know that if we take in more energy than we expend, then we will gain weight, right? We're going to put that energy, store that energy as fat. If we put out more, if we expend more energy than we put in, then you tend to lose weight. But if you're exactly the same, if the energy input is the same as the energy output, then you have this balance and you do not gain nor lose weight. All right. So the input, calorie intake and calorie outtake is basically, so in terms of negative energy, so a negative energy balance is where you have more calories out, so then you lose weight. A positive energy balance is that you actually are taking in more energy than you're using, so you're going to gain weight. All right, so let's talk about the metabolic reactions of the absorptive state. So this is when you have eaten, okay? So you just had a meal and now your body is in the absorptive state. You want to take in those calories and you want to use them as efficiently as you can. So the way your book has broken it down is by the cell. What do your body cells do? What do your liver and muscle cells do? What does your adipose cells do, your fat? And then what does, anyways, it just breaks it down like that. So let's just go look at this flow chart. So here's our small nutrients. This is your glucose, your amino acids. They're in the bloodstream. And what does glucose do? So let's just look at glucose first, right? So glucose is going to enter most of our body cells. And it's going to enter our liver and our muscles. And it's going to also enter our adipose, right? So we're adding adipose here. So it goes to those cells. And most of our body cells will use that glucose for energy, right? ATP. Your liver and muscle, however, they can actually store that glucose as glycogen. So that's a special little trick that your liver and muscle cells have. So out of your liver and muscle, 70% of your body's glycogen is actually stored in the muscle. So the other 24% is actually stored in your liver, and there's some stored in your kidneys. Then we have the glucose going to the liver, and so let's take a look at this box here, right? So when glucose goes to the liver, it can store it as glycogen, but it can also convert, looking at the fatty acids here. The adipose, let's talk about glucose and adipose. So when glucose goes to adipose, your adipocytes can actually store glucose, change it to triglycerides. So glucose that diffuses into adipocytes is converted to fat, all right? So when you eat sugar, but it doesn't contain fat, your fat cells, your adipocytes can actually take that sugar and make it into fat because you're just changing the form of the energy, right? But you do get fatter. If you just eat sugar, you can actually get fat or create fat. If we look at fatty acids, when fatty acids go into your liver and your adipose tissue, they make fat, right? So your liver can actually convert the glycerol. So again, remember fat is a glycerol head and 3 fatty acid tails. The glycerol portion of that fat, your liver can convert that into making a new triglyceride. Fatty acids as well, right, combine to make the triglyceride. When we take a look at the amino acids, right, the proteins will go into your liver, and the liver will actually take those amino acids. They can be intermediates of the cellular respiration, but they can also create fatty acids, all right? And then the proteins go into muscle and all of your other cells, and they again are used to make proteins. So your other, we talked about this in just the other slide. So your amino acids can be put together to make proteins that the cell needs. The turnover for proteins is very quick. And then your muscles, obviously, if you're building muscle, you can actually build more muscle with that. But that's, the flow. So your cells will take those nutrients, and this is a flow chart of how they are absorbed. Okay, so one word on the fatty acids. So if you look at adipocytes in the absorptive state, the initial form that the fat is in is called a chylomicron. And the chylomicron is formed in the jejunum portion of the small intestine primarily, and that is what's going to enter into the bloodstream. And then the LPLs, those enzymes, are going to catabolize those triglycerides that are in those chylomicrons. All right. So let's take a look at the next slide. All right, so here's your energy stores, right? So we talked about how your skeletal muscle and your liver can store glycogen. And about 70% of the glycogen in your body is actually in skeletal muscle. And remember, though, that your skeletal muscle, the glycogen that's in your skeletal muscle, does not leave the skeletal muscle itself. So the glycogen, when it's broken down through glycogenolysis, the sugar, right, the glucose, is actually just trapped in the skeletal muscle cell itself. So the skeletal muscle uses its own glycogen stores. It doesn't share it with the body, but the liver does share. So the liver, which contains about 24% of your glycogen stores, is able to break down that glycogen to sugar, and then that sugar can leave the liver cell and enter the bloodstream for other cells. If we look at your triglycerides, not too surprising that you're finding all your triglycerides in your adipose tissue. And then proteins, the major source for proteins is going to be your skeletal muscle. Okay, so if you are at that point where you're breaking down protein, I hope you're never to that point, right? I had a professor that was joking about, like, what mile on the marathon are you starting to break down your own protein? Because if you're running the marathon, you're going to be using all your glycogen stores, then you're going to be fat, you're going to use all the fat, and then third step, you're going to be using your protein. Anyways, but if it comes to that point, right, then you're mining your skeletal muscle for protein. That's where your protein stores are. All right. How about the post-absorptive state? So when you talk about the absorptive state, I have in the top, it's also called the fed state. So you have just eaten, you're actively absorbing nutrients, and your body is saying build, 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 right? We got the building blocks, store it away, right? Build glycogen from glucose, build fat, build protein if you can, okay? But then the opposite is if you're fasted, this is the catabolic state or post-absorptive state. So now just think about being hungry, low on energy, low on fuel, and your body is going to shift into this other state where you want to start breaking down your energy stores, right? So these stores that we just talked about, we're storing our energy as glycogen and triglycerides. Now that we're starving, we want to start to break those down. So this is catabolic, right? So our post-absorptive state is a catabolic state where we're just breaking down large molecules into the small molecules. So what's interesting here, before going through the flow chart, is that your central nervous system only uses glucose for energy. So it cannot use fat, it doesn't use amino acids. So your body has evolved to give the glucose in the blood to the central nervous system, to the brain and to the spinal cord, right? Because those are so important for survival. The other tissues are going to move and use fats and amino acids, okay? So if you look at body cells in general, oh, by the way, what I just talked about was called glucose sparing, right? Most tissues will turn to other sources of energy other than glucose so that glucose is available to the central nervous system. Body cells in general will use triglycerides or fats, right, as a form of energy. The skeletal muscle has its own glucose stores. That's nice, right? Glycogen. Let's actually start looking at this flow chart. So here's our stored macromolecules. Okay, so let's take a look at muscle, right? So here's muscle. Muscle has its own glycogen. So when it's, breaking down the glycogen into glucose, glucose is used in cellular respiration. So it can be, broken down to pyruvate in glycolysis for cellular respiration, or if your muscles are working and they're working hard and you have anaerobic respiration, then that glycogen, or it can be formed into lactate. So this is going to, if you do produce pyruvate or lactate and they build up in the muscles, they can actually leave the muscle tissue, come into the liver. So here's our liver block. I just want to show you how this is. It's kind of a strange flow chart. And in our liver, right, the liver can then take that and put it into the bloodstream. Okay, you can see this is the blood. Okay, so that's the muscle. Muscle will break down the glucose. And when the muscle breaks down the glucose and you have pyruvate and lactate, so just to go over this again, pyruvate and lactate can actually leave the muscle tissue. So glucose cannot, but pyruvate and lactate can. So they can move into the liver. The liver can form glucose, and then glucose can go into the bloodstream. If you look at liver's glycogen stores, right, the glycogen here can be converted to glucose, which then can enter into the bloodstream, so we can raise our blood glucose levels that way. If we look at our fat, our adipose tissue, we know that triglycerides is the storage molecule here. When we break down fat, we get fatty acids and glycerol. These substances, the glycerol can come into the liver again, and the glycerol can be formed into ketones. The ketones can actually go into the bloodstream. So we talked about ketones as sort of a bad byproduct of, building up, you can become ketoacidotic. However, the central nervous system, if you look here, under extreme conditions, the central nervous system can use ketones. So you can see how the ketone arrow does move into the central nervous system. So the central nervous system uses primarily glucose, but under extreme conditions can also shunt and use ketones as energy. So it's the central nervous system's emergency energy source. The fatty acids here that adipose makes will just go right into the bloodstream to increase the fatty acid content. And then the fats can go into sort of non-nervous, any other tissue in the body can use the fatty acids. Muscle, right? So muscle primarily is your protein stores. The protein can be broken down to amino acids. Amino acids comes into the bloodstream and then kind of does its thing, right? It can go into your non-nervous tissue. Your cells can either use those amino acids as part of the cellular respiration, right, as intermediates in the cellular respiration process to make ATP, or it could use it for other things. But if you're starving, it's probably going to be used for production of ATP. All right, so I think that is it for the post-absorptive state. One word on liver cells here, right? So liver cells can actually create glucose from scratch. So remember that the glucose in liver, yes, you can break down glycogen, but the liver can also undergo something called gluconeogenesis. Okay, gluconeogenesis, making glucose from scratch. So that's what is another process that the liver can do when you are starving. It can actually just make glucose from scratch. All right, so I think we covered the post-absorptive state, the fasted state. And we're going to review with some questions here. So which of the following is not a factor that influences the way in which the body stores and uses energy? Take a look at your choices. And the answer is C, race. All right, which of the following is not, I failed to mention this about metabolic rate at the beginning, but it is in your outline. The factors that affect your metabolic rate, coming back into, where is it? Oh yeah, letter C under energy balance. Just to, because I failed to mention this the first time around, but your metabolic rate is determined by your age, by how much muscle mass you have. So that's why if you want to lose weight, your muscle actually uses more energy than fat does in terms of just how much energy does a muscle cell need to maintain itself versus how much energy does a fat cell need to maintain itself. So muscle cells need a lot more energy to just upkeep the cell itself. So the more lean muscle mass you have, the more energy, just your basal metabolic rate will go up. And so that's why they say for weight loss, one of the best things you can do is gain more muscle mass, because that muscle tissue is just more energy sucking, right? And so you're going to burn more calories just having more muscle. Gender plays a factor in it, your body surface area, in terms of how big you are, right? So if you think about just a large man and a petite woman, the large man just has more cells. He's a bigger person, has more tissue. he's going to need more calories than a petite woman who is going to have just a smaller amount of tissue matter, and just the body just doesn't need that much calories or energy to maintain that tissue. I don't know if you guys have been watching this show called Alone, but it's about these survivalists that go out into the wilderness and they just need to survive on their own. And a lot of their day to day is thinking about how much energy expenditure do I need to do, this task? Where are my calories coming from? And then the larger contestants on this show, that they actually are at a disadvantage because they just need much more calories just to maintain their body than a smaller person does. So the body surface area plays a role, and also the temperature. If it's cold, your body's going to kick up its metabolism just to keep you warm, to keep that core temperature at 37 degrees Celsius. So it's going to expend more calories doing that. So those are some, just going over those issues and about metabolic rate. Looking at the next question here, which of the following is not part of the fate of glucose after it's transported into the cells? So pause it if you want to take a look, think about this. So the answer here is B. Glucagon is a hormone secreted by alpha cells of the pancreas. All right. So if you're thinking to yourself, oh, what was glucagon again? That's a hormone. Glucose is not converted to glucagon, even though the words are very similar, but they have nothing to do with each other. And then, well, they kind of do, but then so everything else is fine, but B is a correct answer there. Where do most of the proteins mobilized for energy usually come from? If you're mobilizing proteins for energy, your biggest source of energy protein store is skeletal muscle. Which of the following describes the form in which lipids are absorbed from the GI tract? So the answer here is letter B, monoglycerides and fatty acids. And they come in the form in chylomicrons. Those, of course, are broken down by lipoprotein lipase. Okay. Which of the following does not store excess glucose, fats, or amino acids present in the body during the absorptive state? Okay, so the answer here is your kidneys. Which of the following statement about the post-absorptive state is not correct? Think about it. Pause it if you want to think about it. Okay, so post-absorptive is going to be after you eat. So this is going to be you're starving. Okay, so is it going to be primarily catabolic? Yes, it is. This is okay. Is primary function is to maintain plasma glucose levels? Yes. There is a cessation for nutrient absorption? Yes. And insulin is actively secreted? No. So so this is the answer, right? If you're starving, insulin is only secreted when you are just eaten. So your insulin is going to kick in during the absorptive state, and it's going to allow cells to take in the sugar to start building. So it's when you're absorbing food, insulin is secreted. When you're post-absorptive, insulin is actually inhibited. All right, so that's the end of part 1.